Well, hello everyone. In this lesson, we will be talking about exponential functions, the domain and range of exponential functions, and how to convert other bases to base e. And finally, we talk about the inverse of exponential function. Now, if we recall the exponential function f of x is equal to e to the x, we remember from the last lesson, this is a one-to-one function. This is very important because now we can convert other bases to base e. For example, if a number 3 is equal to e to the r, then there's only one value of r that satisfies this relationship. So then 3 to the x equals e to the r to the x, which is equal to e to the r times x. More generally, if any number a equals e to the r, then a to the x is equal to e to the r to x, which is equal to e to the r times x. And that is from a property of exponents. So there is no need for a base a, just a base e, because now we can write any exponential in terms of base e. Now let's shift gears a little bit to talking about domain and range of exponential functions. Now look at the example, find the domain and range of the function f of x is equal to e to the negative x plus 7. Now the domain of this function is all the possible values of the x value which it can take. In this case, there are no restrictions on the domain right here, because e to the negative x is just 1 over e to the x, and e to the x can take on all values. So there are no restrictions on the domain. So no restrictions on the domain means that your domain in interval notation will be negative infinity to positive infinity. Now, let us look at what will happen to the range. Remember last time we talked about exponential functions. We said that this plus 7 right here, or the plus k, was your asymptote, was your new asymptote, right? So that's your new asymptote, where if we think about the old asymptote going from, was at the x-axis. So this plus 7 or plus k was your new asymptote. Which means that because this is a function which was above the x-axis to begin with, and we shifted it up 7, then our range will begin at 7. And because 7 is an asymptote, it will not include 7, so it goes from 7. The function goes from 7 to infinity. Right? Now let's talk about exponential growth. Let's talk about exponential growth. Exponential growth diagram looks like, or y to the e of e to the x diagram, where the function, or the graph of the function, it rises as we go from left to right. That's the important thing. It rises as we go from left to right. Usually there are not really any negative values there, but this diagram just shows that it's rising as it goes from left to right, and it is getting steeper and steeper, right? In this case, the k is positive, k is greater than 0. So if you have e to, let's say, any number that's bigger than 0, then any positive number, then it's a growth rate, right? It's a growth, exponential growth. Okay, let's do a pretty quick example. The growth rate of a population is 2.5% per year. The growth rate of a population is 2.5% per year. If the population has 300 individuals, so that is what you begin with, right? So let's say that was a sub 0 equals 300. K will be equal to 0.3 0.025, that's 2.5%. We write the k as a decimal, okay? And we want to find out how many animals will there be in 5 years. So t equals 5 years. T equals 5. Now what we want to do is that we want to find a of t, which is a of 5, equals a sub 0, which is 300, e raised to the 0.025, and that's times 5. And this we will plug into our calculator and then see what comes out of that, okay? So we plug that into a calculator, and then what comes out of it should be 339.94. So because we're talking about animals, we don't want to say 339.94 animals, so let's round it up a little bit to 340 animals. All right, and that's it. Okay, or individuals. Let's talk about exponential decay. The decay rate of carbon-14 is 0.0000121 per year. What percentage of carbon-14 will remain from a sample of 100 grams after 10 years? And we're using the formula A of t is equal to A sub 0 E negative 0.0001121 t. Now, this negative here comes from our decay formula, where we said A of t was equal to A sub 0 e to the kt. But in this case, because k is a decay, then it is less than 0. So we got to use a negative to show that it's less than 0. So let's see what we have here. Our k is 0.00121, 0.00121. Right, but we're going to make that negative. The decay rate is given as a positive, but when we plug that in, we will put it in as a negative number because it's decaying, right? Or we can say the formula is negative kt if you look at a different formula from the one that we're using, but the one that we're using has e to the kt. So in order to make it be a decay or a graph be decaying, you need a negative sign. Okay, so the A sub 0 is equal to 100, right? T equals 10, okay? And you're asked to find what percentage of the carbon-14 will remain after 10 years. Heads up, for a percentage left question, you need not have been given an original amount. The question could just have been left where you could choose your own initial amount. For an amount left question, you will be given an initial amount. So bear that in mind right now. Okay, so we want to find A of 10 equals to A sub 0, which is 100. E to the negative 0.000121 times 10, and that you plug into your calculator, and you should get 99.879, a whole bunch of decimals, which we will approximate to 99%. That should be 98.87. Now we approximate that to 99%. Right? Okay. Now, let's talk about finding zeros. Finding zeros are finding x-intercepts. And these we get some exponential functions, which probably are a little bit tricky because we have to factor out some stuff. So what we want to do is the x-intercept is where y equals 0. So we want to set the side equals 0 and then factor the parts on the right side. So let us factor out a couple of things and see what is happening right here. Now, let us say there's an x raised to the 7 here, but there's an x raised to the 6 here. So the common thing in both sides would be x to the 6, right? So x to the 6, and then what will be left here is x. Then e to the 8x is common, so e raised to the 8x. And then what will be left on this side now is 8, and then there's an x, so that's 8x. And what's left on this other side of the plus sign is a 7. All right, so if these two parts is equal to 0, then either this equals 0 or this equals 0, or both, right? So if this part equals 0, then that means x equals 0, right? And the other solution is 8x plus 7 equals 0. So that means x would be equal to -7/8. So those are your solutions, right? So your solution is -7/8 and x equals 0. So that's it for finding zeros. Now let's talk a little bit about the inverse of an exponential function real quickly. So the inverse of an exponential function, we recall f of x equals e to the x is a one-to-one function. And if there's a number b is equal to e to the x, you can find x, right? This is a bit complicated because we need to find an inverse and have a notation for this inverse. So let's do a setup. Y is equal to e to the x, so the exponential of x, or exp of x. If y is equal to exp of x, then x is equal to the inverse exp of y. We need to call this inverse some name, so we call it the natural logarithm. So if y is equal to e to the x, its inverse is x equal to ln y, right? So recall the properties of exponential functions applied to exponential functions. E to the a times e to the b will be equal to e to the a plus b. So it's same base, you multiply, then you add the exponents, right? E raised to a times b is equal to e to the a times b. And then e to the a over e to the b is equal to e to the a minus b, right? Notice a and b are real numbers. Now what about natural logarithms? Suppose that y is equal to e to the x, which is the same as exp of x. Then, equivalently, ln of y equals e to the x. And if we take the exponential of a log function, that gives us x. So exp of ln x is equal to x. Then ln of exp x equals x. That's because they're inverse function. All right, notice when we did inverse functions earlier on, inverse functions composition always returns x, right? With x is the input each time. Now e to the x, y equals e to the x implies x equals ln y. A equals e to the b implies b equals ln of a. If c equals e to the d, then implies d equals ln of c. Then if a times c equals e to the b times e to the d, which is equal to e to the b plus d by the law of exponents, then ln of a times c input equals b plus d, and then that will be equal to ln of a plus ln of c. So we can apply this here to something like ln of 15 equals ln of 3 times 5, in parentheses equals ln of 3 plus ln of 5, and e to the 5 times e to the 3 equals e to the 8. We add the exponents. And then a equals e to the b, and b equals ln of a to the r is equal to e to the b times r equals e to the r times e. So ln of a of r is equal to ln of e to the rb. That means rb equals rb. Then ln of ar is equal to r ln of a. So ln of something like 4 squared equals 2 ln of 4. And ln of 5 times 6 cubed will be ln of 5 plus ln of 6 cubed, which is equal to ln of 5 plus 3 times ln of 6. And